Okay, hello, Year 12. What we're going to be doing today is looking at the topic of redox chemistry. This is because I'm off this week for a lot of the lessons, you're off a lot of the lessons this week. So I'm going to do a little bit of talking through what redox chemistry is, and then I'm going to set you some tasks to do for next week. So, firstly, what is redox chemistry? Well, the word redox it's a portmanteau, so smashing together of two words are the words meaning reduction and oxidation. So we've just taken these two words and smashed them together, a bit like the word spork is a spoon and a fork, etc., etc. This is redox chemistry. So a lot of chemical reactions are redox. Many chemical reactions are redox, but not all. Not all chemical reactions are redox reactions. So we need to find out what a redox reaction is, and then we need a way really of deciding which chemical reactions are redox and which ones are not. For example, I know just off the top of my head that neutralization reactions are not redox reactions. So there's things that I know that we can we'll all try and we'll look at and we'll find a way of working these things out. Sorry, I'm waffling my words a little bit. Let's just get on with it. So reduction and oxidation. Well, you'll have done this a little bit at GCSE before. You'll come across this mnemonic, oil rig, and this mnemonic tells us that oxidation is defined as being loss of electrons. Now, originally, oxidation was just to do with the element oxygen, but then it was found that there was a more useful generalization of the term oxidation. Whenever something lost electrons, we started to call this oxidation. So you'll know as well that oxidation is when something gains oxygen. That is true, but oxidation is also defined as being loss of electrons. Reduction is gain of electrons. So what we're describing here is redox reactions are reactions where something loses electrons and something else gains electrons. You cannot have loss of electrons without something else gaining them. Electrons can't just disappear. Hence, any chemical reaction where loss or gain of electrons has happened is described as being a redox reaction. And many reactions in chemistry are redox reactions. They involve the movement of electrons. All right. So these are just some little reminders of things that we've done prior. So what we need to do then is we need to be able to spot when electrons have been lost or gained. Now, I'm going to give you an example from GCSE. You might be given this at GCSE. They might tell you that copper 2+ reacts with magnesium to form magnesium 2+ and copper. This is an example of a displacement reaction. For example, this could be copper 2+ in the form of copper sulfate solution, and it forms magnesium sulfate solution, or whatever. But copper 2+ reacts with magnesium to form magnesium 2+ and copper. Now, I think this is quite clearly a redox reaction. This is a redox reaction because we're looking at what's happening to each of these elements. If we look at what's happening to the copper, we can see that the copper 2+ becomes copper, and we can see that the magnesium the magnesium becomes magnesium 2+. So this equation that I've written here is what's known as an ionic equation, because we've got rid of the spectator ions, we haven't used any sulfates. This is an ionic equation. And these green arrows that I've drawn on here, this green arrow describing the story of magnesium, and this green arrow describing the story of copper 2+. We can write these green arrows as what we call half equations. So here's the copper one. I can write a half equation that says copper 2+ becomes copper, and magnesium becomes magnesium 2+. So one of the skills we'll be looking at today is we'll be writing these things called half equations. I'm just going to balance this one now. If copper 2 plus becomes copper, the only way it could have done that is by gaining 2 electrons. So this is a half equation for copper 2 plus becoming copper. And magnesium to become magnesium 2 plus, it must have lost 2 electrons. So we're going to stick these electrons over here. These are ideas that you could have come across at GCSE, and these are called half equations. And what we can see is in this reaction above, the one that I drew out in full, this is a redox reaction because something lost electrons, something gained electrons, the copper 2 plus gained electrons, and the magnesium lost electrons. So we've had gain of electrons, we've had reduction of copper 2 plus, and oxidation of Mg. This is a redox reaction. Right, so it's an example of a redox reaction where we can see, if we look at the individual elements, we can see that electrons have been lost or gained. What we are going to do today, so now that was actually quite a long introduction. What we are going to do today is we're going to learn a few skills. We are firstly going to learn the skill, something called oxidation states. At first, it will seem confusing. You will do this. At first, it will seem confusing. Then you will be able to work out oxidation states, but you won't know why you are working out oxidation states. And then we will be able to apply this knowledge, and you will see how knowing how to do oxidation states will help us to decide whether a chemical reaction is redox or not. So believe me, you're going to be confused. You're going to be skilled up but confused, and then eventually you're going to be skilled up and less confused, hopefully feeling pretty good about things. I'm actually going to just demonstrate me using oxidation states right now. So you won't know quite what I'm doing, but this is what you're going to do in a second. I'm just going to write an equation. I've got one underneath here. I'm going to give me 1 second. All right, I'm going to write this equation: Na2O plus H2O. Actually, that's probably a bad example. I'm going to do this one. 2Na plus 2H2O makes 2NaOH plus H2. So I want to know if this is a redox reaction. I am about to do something called oxidation states, or oxidation state analysis. This is what you're going to be able to do. 0 plus 1 plus 1 minus 2 minus 2 plus 1, 0. Sodium from 0 to plus 1. Hydrogen from plus 1 to 0. This is a redox reaction. Sodium has gone from 0 to plus 1. That's oxidation. Hydrogen has gone from plus 1 to 0. That is reduction. The sodium has been oxidized, the hydrogen has been reduced. Now, wouldn't you like to know how to do that? Well, that's what we're going to learn. All right, the first thing I did there is I drew some little numbers underneath. These are called oxidation states. Once I looked at the direction these numbers took, whether they've gone from pluses and minuses, I could then decide whether or not it was a redox reaction. I'm just going to pause this 1 second. All right, so we're going to learn how to do these things called oxidation states. Once you can do oxidation states, we'll be able to do this sort of analysis, and that's the plan for today. I just had to pause the video there because GCSE chemistry just finished, and they wanted to come and tell me how it's gone. And it had gone well, apparently. Right, so you're going to get this sheet. This is from Chem Sheets. And the first thing it's got is this title called oxidation states. So this is all part of redox chemistry, reduction and oxidation chemistry, oxidation states. Remember what I've said? Lots of chemical reactions out there involve the movement of electrons, and they're called redox reactions. There are some chemical reactions out there that are not redox, and we'll be able to find out. We'll be able to quickly deduce whether something is redox or not once we learn the skill of oxidation states. All right, now there are some rules for assigning oxidation states. You saw that I could do this very, very quickly on here. The rules for assigning oxidation states. Now I'm going to use the ones off chem sheets, but I'm going to add some other ones in as well. Okay, so in elements, the oxidation state is always 0. So this is chlorine, the element. So I would say the oxidation state of chlorine in an element is 0. In fact, let me just introduce this idea. I'm going to read this top section. When using oxidation states, we effectively imagine everything to be an ion. The oxidation state is the charge that a species would have if it was an ion. So what that means then, the oxidation state of 0 is effectively saying this element here has got all of its normal electrons in its outer shell. It hasn't lost or gained electrons. So the oxidation state of chlorine, the element, is 0. The oxidation state of hydrogen, the element, is 0. The oxidation state of sodium, an element, is 0. Look at the example I did a minute ago. Sodium, that's elemental sodium. It's not sodium plus or sodium in a compound. So I just put 0 underneath here. And look what I did at the end as well. Hydrogen, 0. So whenever I see an element, I'm going to write 0. The oxidation state of carbon solid. So for example, the oxidation state of carbon in diamond is 0. Hopefully you get the idea. So that is rule number 1. The oxidation state of elements is 0. This will be fine in a minute. We've just got to learn this skill. Remember, we're going to learn a skill. We're not going to know what we're doing. Then we're going to learn a skill, but we still don't know why. All right. So, next bit. In simple ions, the oxidation state is the charge on the ion. So this is easy. A copper 2 plus ion has an oxidation state of +2. Notice, it's a 2 plus charge. We say +2. The oxidation state of chloride, Cl minus, is -1. Easy peasy. Aluminium oxide is an ionic compound. We know that in an ionic compound, oxide ions are -2. If you've got 3 oxide ions, the aluminiums must be +3. Hopefully you realise that. If you've got aluminium +3 and +3, that makes +6. And you've got oxygen -2, -2, -2, that makes -6. It all balances. So if you go back to that one that I did a minute ago, oxidation state in sodium hydroxide, sodium ion is +1. Actually, I'll come to these ones in a minute, but that's where I got the +1 from. So, the next little bit is the total of all the oxidation states must equal the overall charge on the species. I'm going to come back to that one in a second. All right. Here are some very common oxidation state rules. Hydrogen in a compound is nearly always +1. Nearly always +1. Oxygen in a compound is -2. Any group 1 element in a compound is +1. Any group 2 element in a compound is +2. So these are some really, really important rules. So the way I'm going to show you this is just by doing examples, and we'll come back to this one in a minute, where the total of all the oxidation states must always equal the overall charge on the species. All right, I'm going to give you some examples. So what we've got here is CH4. If I'm asked to give the oxidation states in CH4, I look through my rules. All right, CH4 is not an element. I'm just going to have to pause it again. Okay, CH4 is a compound. CH4 has no overall charge. So what I've got here, I'm going to look for any rules. I don't have any rules for carbon, but I do know a rule for hydrogen. Hydrogen is nearly always +1. So what we've got here, we've got 4 hydrogens that are +1. And I'm going to give you a little number line thing to look at here. I've got CH4. I know that overall CH4 has a charge of 0. So just watch this on a number line. You won't need this number line for long. I know a rule that hydrogen is nearly always +1, and I've got 4 of them. So imagine this situation. You've got +1 because you've got 1 hydrogen. You've got +1 because you've got another hydrogen. You've got +1 because you've got another hydrogen. And you've got +1 because you've got another hydrogen. All right. My carbon must have an oxidation state that takes me back down overall to 0. So my carbon must be in an oxidation state of -4. So the rule I've used, hydrogen is +1, and there are 4 of them, so that takes it to +4. The carbon must be, in this case, case, -4. What this means is that the carbon here has effectively gained 4 electrons. This is what we're using these oxidation states for. All you need to know though is, can you work out the oxidation state? Let's try another one. You'll still be in this stage now, confused, I imagine. All right, carbon dioxide. If somebody asks me what are the oxidation states of carbon and oxygen in carbon dioxide, so CO2. All right, I know some rules. I know that oxygen in a compound is nearly always -2, and I can use this rule to work out the oxidation state of carbon. So I'll do the number line again. Overall, carbon dioxide has got a charge of 0. There's no overall charge on it. Oxygen is -2, and there are 2 of them. So -2, -2 takes me down to -4. That means the carbon, in this case, must be +4. Oxidation state of carbon in here is +4. That's where these numbers come from. I'm going to go across to H2O now. What are the oxidation states of hydrogen and oxygen in H2O? H2O. Well, we can just use the rules here because I know a rule for oxygen. Oxygen is -2, and I know that hydrogen is pretty much +1. This works. If oxygen is -2, overall it's 0. The hydrogens must be +1, +1. This one works. Na2O. Let's have a look at Na2O, this one here. All right, the rules. Sodium is a group 1 element, so it's going to be +1. Oxygen is -2. This one works as well. Oxygen is -2. The sodium must be +1. That's why the whole thing overall is 0. It's +1 and +1 and -2. So oxidation states are a little bit like charges. If it's an ionic compound, we can just use the charges. If it's a covalent compound like these, we're going to just apply some of the rules. The rules being, hydrogen is nearly always +1, oxygen is -2, group 1 elements are +1, and group 2 elements are +2. All right, we still haven't really looked at this one yet, and that's where we're going to do some of these examples. So what you all have now is this sheet in front of you, and we're going to work through these examples together. All right, question 1 is going to be working through the examples. I might ask you to pause the video at certain times. Question 2, you're going to go through it. I'll pause the video, you pause the video, and then I'll go through all of the answers. You have to make sure you understand each of these before we go on. All right. So, there is another rule at the bottom here. In molecules and more complex ions, the more electronegative element is assumed to be the negative ion. All right. We'll come to that in a second as well. Right. This is the bit. This is where we're really getting into it. We're 18 minutes in, and I'm going to start giving some examples now. What we're going to be looking at is, can you assign oxidation states? You are not allowed to skip this skill. It is vitally important. All right then. Iron. Elements. There's the rule. It's an element. It's 0. Iron chloride. Right, well, this is an ionic compound. It's made of iron ions and chloride ions. Chlorides are pretty much always -1, aren't they? All right, that's a decent rule on chloride ions. So if we've got 3 chloride ions that are each -1, I'll do this number again, this number line, 2, 3, -1, -1, -1, the iron must be +3. All right, fairly straightforward. This is FeCl2, an ionic compound. The chlorides are pretty much always -1. That's a rule about chlorides, but we'll come to that in a second. The iron must be +2. All right, iron +2. Now then, we've got a slightly more complicated something going on here. We've got potassium, iron, and oxygen in a compound. So I'm going to try and apply some rules now. I know a rule. Oxygen is always -2, or pretty much always -2. Potassium in an ionic compound is +1 because it's a group 1 element. So what I've got to decide now using this information is what is the oxidation state on the iron. All right, I have got 4 oxygens that are each going to be -2. I'll do it on a number line. All right. So overall, there's no charge on this compound, so it's 0. I've got 4 oxygens, -2, -4, -6, -8. -4, -6, -8. My oxygens take me down to -8. I've then got 2 potassiums that are +1. Boop, boop. That takes me to a position of -6. Therefore, the ion must be +6. So 4 oxygens, that takes me to -8. 2 potassiums takes me back up to -6. This must be +6. You pause, you make sure you understand what I'm doing. You watch this bit of the video back until you can do that. All right, this one, slightly more interesting. You've got something in square brackets known as a complex. All right, very straightforward way of doing this though. This is iron surrounded by 6 water molecules. We do more of these in year 13. A water molecule is neutral. So I'm just going to cover that up with my finger or with a pen. Makes it very, very straightforward. This is an iron 2+ surrounded by 6 water molecules. You don't need to necessarily go into great detail in your understanding. What you've got here is iron surrounded by 6 neutral water molecules that don't have any overall charge. This is just an iron 2+. So I'm going to put the oxidation state +2. The next line, chlorine. Chlorine, a non-metal, but chlorine or element, chlorine goes around in pairs, 0. Oxidation state in chlorine is ClO3. Now, I've used the idea that chlorine is -1 in all of these examples up here, or both of these examples here. However, the final rule is, in molecules and complex ions, the more electronegative element is assumed to be the negative ion. So when chlorine is bonded to oxygen, the rule about oxygen beats the rule about chlorine. All right, so what we've got here is chlorine and oxygen joined together, and oxygen's rule, -2, is more important than the chlorine rule, -1. Oxygen is one of the boss elements. It's very electronegative. All right, so what we've got here is we've got to work out the oxidation state of chlorine in this molecule, or in this little ion here. All right, I'm going to draw my number line. Overall charge on this ion is -1, so there's 0, is -1. This is my target. I don't want to get back to 0. All right, I've got 3 oxygens. Each of those is -2, so -2, -4, -6. So -2, -2, -2. And my chlorine has got to get me back up to -1. Well, actually, let me just draw this again. So there's 0, -2, -4, -6, -2, -4, -6. I've got 3 oxygens, so that takes me down to -6. My chlorine has got to get me back up to -1. So my chlorine must be +5. 3 oxygens, that takes me to -6. The chlorine, if that's +5, that's why overall it's a negative charge. ClO-. All right. So ClO- is, you've got oxygen, so that's going to be a -2 rule. And my chlorine must take me back up to -1 overall. So overall this has got to be -1, and my oxygen we know by a rule is -2. So my chlorine in this case must be +1. If you're unsure, there's a number line. My oxygen takes me down by -2. My chlorine must be +1 because overall the charge is -1. Now we've got Cl2O7. Cl2O7. All right, I'm going to ditch the number line now. I know that the rule for oxygen is -2. So if I've got 7 oxygens, I'm taken down to -14. Actually, I'm not going to ditch my number line. I'm going to do one more number line for this one. Cl2O7. Overall, there's no charge on this. So I'm going to 0. 07 times takes me all the way down to -14. -2, -4, -6, -8, yeah, okay? Now I've got 2 chlorines that are going to take me back to 0. Boing, boing. Each one of those must be +7. All right, the chlorine here is +7. Cl2O3, there's my number line. I've got 3 oxygens. -2, -4, -6, so that takes me down to -6, and I've got 2 chlorines to take me back to 0. Each of these must be +3. All right, +3. Now, let's have a look at this really interesting thing about chlorine. Chlorine here is chlorine with all of its electrons. We know up here that chlorine likes to become chloride. Very commonly, chlorine likes to gain an electron. That's what that number -1 means. This means in these compounds, chlorine has become a chloride. It loves that, it gets a full outer shell. But the interesting thing about chlorines, chlorine is actually also able to lose 5 electrons. If you look at its position in the periodic table, it's the 5th element in the P block. It's quite happy to lose 5 electrons. It can also lose 1 electron. It can also lose up to 7 electrons, so all of the electrons in its outer shell. In this compound, that's what it does. And it can lose 3 electrons as well in Cl2O3. So what we say here with chlorine, it has variable oxidation states. All right. Remember the rule about chlorine. Chlorine in a compound is pretty much always -1. But when we join it to oxygen or a more electronegative element, it looks like it can do lots and lots of funky stuff. All right. So we should still be a little bit confused, but we are assigning numbers to elements inside compounds. All right, what I'm going to do now, normally in the lesson I would say, right, everybody get on with this activity, let's see how you do. What I'm going to do now is I'm going to ask you to pause the video and I'm going to go through these oxidation states. This will be the end of my first video. This is when you would do 20 minutes work. So I'm now going to go through all of these answers. Please don't just write my answers in. You should pause the video now and then you can see me explain each one. All right? So, SO2, sulfur dioxide. I'll tell you a little bit about each molecule. Sulfur dioxide is a choking gas. It's got no overall charge. So we're just going to apply a normal rule then. We look for what rules we've got. We've got some oxygens in there. Oxygens are -2 in a compound. If you've got 2 oxygens, -2, -4, the sulfur in this must be +4. What this means is the sulfur in SO4 has effectively lost 4 electrons. That's interesting. All right? So, S8 is sulfur, the element, 0. SO3, well, we know that oxygen is -2, so that's -2, -4, -6. The sulfur must be +6. The sulfur in here has effectively lost 6 electrons. Let me just write the electron configuration of sulfur. Sulfur is neon core 2s2, sorry, 3s2, 3s2, 3p4. So the sulfur in SO3 has effectively lost all of these electrons. Its outer shell electrons, it's in group 6. The sulfur here in SO2 is effectively +4. It's lost its p electrons. What I'm trying to suggest this here is there is a link between the oxidation states you can have and the electron configuration. You don't need that for A level, but you might need it if you're doing the Cambridge Chemistry Challenge. All right, H2S, hydrogen sulfide, smells of eggs. All right, we look for the rules. There is no rule about sulfur, but there is a rule about hydrogen. Hydrogen is +1 when it's in a compound. If we've got 2 +1s, this must be -2. So the sulfur in this is -2. Well, that makes sense, doesn't it? Because sulfur is 3s2, 3p4. It's a group 6 element. It's got 6 electrons in its outer shell. Yeah, of course, it's also quite happy to to gain 2 electrons. So we're seeing here that sulfur can lose 4, lose 6, or gain 2. Don't be surprised that sulfur can be -2. It's in the same group as oxygen. All right. NH3, I don't know any rules about nitrogen, I just know that it's in group 5. If an element is in group 5, that suggests if you're in group 5, you're probably quite happy to gain 3 electrons. But we've also seen it could mean that you can lose 5 electrons. So we'll see. We know the rule for hydrogen, +1. If you've got 3 pluses 1s, we've got 3 +1s, that means the nitrogen must be -3. Moving on. Oxygen, the rule for oxygen is -2, so that's -2. 2 oxygens, -2, -4. The nitrogen here must be +4. Nitrogen apparently can lose 4 electrons. That's surprising, but it's happening. NO3 minus. So we know that oxygen is -2. There we go. I'll put the rule down first. One of these must have a rule attached. So -2, -4, -6. The nitrogen must take me back to overall -1. The nitrogen must be +5. All right. Nitrogen, the element, 0. KCl, ionic compound, Cl minus, potassium plus 1. My lights have gone off in the room because I haven't moved. SO4, 2 minus. Oxygen is minus 2. There are minus 2, so there are 4 of them. Minus 2, minus 4, minus 6, minus 8. Sulfur's going to take me back to minus 2, so the sulfur must be plus 6. All right, I'm going to go through these a little bit quicker, maybe. All right, Na2CO3. Right, I don't have a rule for carbon, so that's going to be the tricky one to work out. Oxygen is minus 2. Group 1 metal is plus 1. That's forgotten that quite a lot. So, oxygen minus 2, minus 4, minus 6, and I've got 2 sodiums that are plus 1. The carbon must be plus 4. I'm going to do a number line for that. All right, sodium carbonate. All right, sodium carbonate. Target is 0 because there's no overall charge. 3 oxygens, minus 2, minus 4, minus 6. So my oxygens take me down to minus 6. My sodiums are plus 1. That's a rule. Plus 1, plus 1. That takes me to minus 4. The carbon must be plus 4. The carbon, the oxidation state of carbon in this compound is plus 4. It has effectively lost 4 electrons. Right, Cr2O3, oxygen is minus 2, minus 2, minus 4, minus 6. There are 2 chromiums, and minus 6 for my oxygen, there are 2 chromiums, they must each be plus 3. Be careful on that one. CrO3, minus 2, minus 4, minus 6, so they're each minus 2. This must be plus 6. Then keep going, that's the tone of the break, minus 2, minus 4, minus 6, minus 8. So they're each minus 2. The manganese must be plus 6 to get me back to 2 minus. Manganese oxide, MnO4 minus, oxygen minus 2. The manganese must be plus 7 to get me back to minus overall. All right, we've got break time happening here. Minus 2. The coppers must be plus 1. Star on that, there are 2 of them. Make sure you've got that. Oxygen minus 2. Copper can also be plus 2. So copper can be plus 1, copper can be plus 2. If you did triple science at GCSE, transition metals can have multiple charges. All right, rules. Potassium plus 1, chloride minus 1. There's nothing else, no more electronegative elements in there. The chlorides take you down minus 1, minus 2. The potassium takes you back up 1. The copper must be plus 1. All right, and then we're on here. All right, we have some problems with sodium hydride and H2O2. These are common, these need explaining, right? NaH, you've got 2 options. One rule would be sodium is plus 1 and therefore hydrogen is minus 1. Or is it hydrogen is plus 1 and sodium is minus 1? All right, these are the options. So we either use the rule that hydrogen is always plus 1, or we use the rule that sodium is plus 1 and hydrogen must be minus 1. All right, the one that wins in this case is sodium plus 1 and hydride minus 1. This is an ionic compound. Sodium plus 1, H is minus 1. For this reason, just notice when you've got alkali metals with hydrogen, it's called a sodium hydride, and we form this very stable H minus ion. H minus ion. That is a hydrogen, like that, that's gained an extra electron, it has a full outer shell. Just be aware of these. All right, they're called metal hydrides. This one is slightly unusual. We've got 2 elements in here that both have a rule. We know that oxygen is normally minus 2, and we know that hydrogen is normally plus 1. But these rules don't work together. So I'm going to do the 2 options here. Our options are either hydrogen is minus 2, sorry, oxygen is minus 2, so we use the oxygen rule, and that would mean hydrogen would have to be plus 2. Or we use hydrogen is plus 1 and oxygen is minus 1. All right. You cannot do this. Hydrogen cannot be plus 2 because hydrogen has only got 1 electron. So this must not be the case. It must be that hydrogen is plus 1 and oxygen in this case is minus 1. Examiners love to ask this question. This is a chemical called hydrogen peroxide. I'm going to stop this video here. This video was all about oxidation states, and that was your first task to complete this sheet. All right. In our next task, we're going to have a little look at the back page. Actually, no, so I'm just going to do that now before I grab a coffee. All right, sorry about that. Range of oxidation states. So this is not actually on AQA specification specifically, but this is going to be really, really useful if you're doing your Cambridge Chemistry Challenge. It's a little bit what I've alluded to previously. I'm just going to pause the video. Okay, this last little bit is about the range of oxidation states you can have, and it is limited by the position of the elements in the periodic table. So it's to do with the number of electrons in your outer shell. If you're in group 4, like carbon, you've got 4 electrons in your outer shell. And what this means is you're limited. Carbon can either gain 4 electrons or it can lose 4 electrons. You very rarely find that elements will go beyond that outermost shell. So if you're in group 5, like nitrogen, you've got 5 electrons in your outer shell, and you can either lose all 5, which means you can be a maximum of +5 oxidation state, or you can be in group 5 with 5 electrons in your outer shell, you can gain 3 to get a full outer shell. So the range, notice that magic number 8 that you'll have seen at GCSE. If you've got transition metals, they've normally got positive oxidation states because they're metals. Metals, when they react, they lose electrons. Losing electrons until they reach a group 0 noble gas electron configuration. But we don't often go higher than +7 in practice. When you've lost 7 electrons, it's the remaining electrons inside that atom are going to be so well held by that nucleus, we never see anything losing 8 electrons. All right, you actually get this maximum with manganese. Manganese is the only element that I know of that goes to +7, that loses 7 electrons. If you notice the position across here, 1, 2, 3, 4, 5. Vanadium has a maximum oxidation state of 5. It can lose its 4s and 3d electrons, or 5 of them. Chromium is in the 6th position. It can lose 6 electrons. 1, 2, 3, 4, 5, 6, 7. Manganese can lose 7 electrons. But we don't often see iron losing 8. As we go across here, you might think, because you've got copper in this position and zinc, copper only really exists as +2 and +1. Just because it's got so many protons, it doesn't lose electrons particularly easily. If you're in group 7, we've already seen with chlorine, group 7 likes to be -1. You learned that at GCSE, but we've also learned it can go +7, they can go +5, they can lose electrons. So this little task here is not essential. The main thing from this first lesson is that everybody in my classes can assign oxidation states. We go back to where we started then, and I said, today we're looking at redox reactions. Can't even try much with the paper now. We're looking at redox reactions. Redox reactions are reactions that involve the loss and gain of electrons. And we have done our first lesson on this today then, where we have learned how to write oxidation states. We're not quite sure how it all fits in now, but I promise you that if you can work out oxidation states, we can decide whether something is redox. So that was Redox Lesson 1, for those who are going to miss that lesson this week. All right, I hope that eventually made sense. Right, thanks everybody.